Hello and welcome to another Java tutorial. In this tutorial, I'm going to continue our discussion on special functions, and we're going to look at a very famous function called the error function, and it has a family of functions, the complementary error function, etc. So what is the error function? Now, in order to understand error function, we need to realize that most natural phenomena follow a normal distribution of probabilities. What it means is that if you have a continuous variable, which we call a continuous random variable, all right, typically they have an observable value or an expected value or an average value or mean value, a statistical mean value, and then which is the peak of this probability distribution. And as we get away from this expected value or mean value, the probability density drops. So this bell curve gives us the famous the Bell distribution or the Gaussian distribution. So this bell curve is formally known as the Gaussian distribution. So this is a probability distribution. It has a mean value, this mu, and a standard deviation from the mean value, which is called sigma. So 1 over sigma square root of 2 pi e to the minus x minus mu squared over 2 sigma squared. So mu is a statistical expected value or mean. If you are familiar with quantum mechanics, you know that this expected value or mean value or is also called the observable value, because we typically measure the value that is most likely to be seen, right? That's kind of like our observable value. And then sigma is the statistical deviation from the observable value or this mean value, all right? Now, what is normal distribution? Normal distribution is when the expected value is 0, so this bell curve is centered about 0, right? And sigma is 1, so its standard deviation is 1. And then f of xn, if x is our Gaussian distribution, x sub n means the normal Gaussian distribution. So sigma is 1 and mu is 0, 1 over square root of 2 pi e to the minus x squared over 2. Now, the main property of any probability distribution, be it Gaussian or normal Gaussian, is that they are normalized, in the sense that the total probability is the integral from minus infinity to plus infinity, which encompasses all the possible values for x. Therefore, this should be 1, because these are probability densities. Now, what is the error function? So error function is kind of like the integral of this normal distribution, right? But so its error function, it's a symmetric integral from minus x to x, the normal distribution, but we prefer to scale it a little bit. So instead of directly integrating from minus x to x of the normal distribution, we scale it by square root of 2. So it's the integral of minus x to x of f of xn, the normal distribution, but instead of t, we have a square root of 2t d of square root of 2t. So error function of x is minus x to x, 1 over a square root of pi e to the minus t squared dt. And this is more like a convenient notation, because we don't want to deal with division by 2 in the exponent. So it's basically a nice format, all right? So it's just the integral or the probability for a variable that has a normal distribution, and we want to find the probability from minus x to x, which is the area, but we also define it in a way that we scale the variable, square root of 2. Now, area under normal curve, obviously area under this 1 over square root of pi e to the minus t squared is our error function from minus x to x, right? This is the normal curve. And then obviously we can see that because this was the integral of a probability density, if x goes to infinity, i.e. integral from minus infinity to plus infinity must be 1, right? This is just because of this property. And then if x goes to negative infinity, so if I set x to negative infinity, I end up with plus infinity to minus infinity. and this function is an even function, so this becomes the negative of error function of infinity, which is 1. So error function at infinity, it should reach 1, and error function at negative infinity, it should reach negative 1. All right. And in general, we can see that the error function has an odd symmetry. Obviously, if I replace x with negative x, error function of negative x becomes minus error function of x. All right. So it has an odd symmetry. And again, its relation to the probability is that it was the integral from minus x to x of the normal distribution. But then in most cases, we end up using something called the complementary error function, which means we are interested in knowing the probability from x to infinity instead of minus x to x. And obviously, you can see that if I add up 0 to x plus x to infinity plus 0 to minus x to minus infinity, because of the symmetry of the normal curve, I end up with 1. So the area under the curve for these two white areas from x to infinity and from minus x to minus infinity is the probability where the magnitude or absolute value of t is greater than x. And that's just 1 minus this blue area, which was the error function. So the complementary error function is just 1 minus the error function. And that gives us the probability of our variable x being outside a given range from minus x to x. So the probability of t is less than x, the magnitude, which means t is between minus x to x, is error function of x. The probability that t, magnitude or absolute value, is greater than x, which is these two white area from x to infinity, from minus x to minus infinity, is the error function complementary. So the complementary error function and the error function, they just add up to 1 always, right? Now, how do we implement error function in Java in a very efficient way? So a small argument expansion, again, we always look for power series and the power series that converge to the value of the function. And typically we have the power series about x equals 0, which is a Taylor or Maclaurin series. And here I have this power series, and it works very well for x magnitude less than 4, so x between minus 4 to 4. We have 2x over square root of pi, sum from 0 to infinity, minus 1 to k, x to the power of 2k, k factorial, 2k plus 1. Now, this is very similar to what we had for Bessel functions. In Bessel functions, we had the gamma, which represents some sort of factorial. But then we're not going to calculate each term of this series first and then add them up, because we have expensive operations such as k factorial and x to the 2k. So a power and a factorial, these are extremely expensive operations. So how do we sum this up to n terms? So we do the clever summation exactly the way we did it for Bessel functions. So first of all, we can write this summation, this series, in a very clever way. So at k equals 0, the value is just 1. At k1, it's minus x squared over 1 factorial, which is 1 times 2 times 1 plus 1, which is 3. All right? And then we factor this x squared over 3, and then write the other terms with this term factorized from them. So if I factor this out, k equal 1 becomes 1, and then k equal 2 becomes x to the 4th, but I already have factored out x to the 2. So I end up with x to 2, and then I have 2 factorial, which I already have factored out 1, so I end up with 2, and then 5, but because I have factored this whole term, there is a 3 in the denominator, so I have to add a 3 in the numerator. So when I multiply, k equals 1 is x squared over 1 times 3, k equals 2 is minus times minus, which is positive, x to the 4th divided by 1 times 2, which is 2 factorial, 3 times, and then 3 cancels out, I end up with 5. So this gives me the correct term, and obviously if I want the nth term is basically x to the x squared. Again, the good news here is that we don't need to calculate x squared each time. We just calculate it once which is again more efficient way of doing numerical calculation of this series. So we're trying to squeeze as much efficiency and performance in computation as possible. And then it's basically 2n minus 1 over n times 2n plus 1, something like that, right? The nth term. So how did I implement it? In a very efficient way in Java. So we have this private double error function, a small argument for a double x. So we have this lead term 2x, 2 over a square root of pi times x, right? So it's there. And then val, our val is x squared, which is common in all these factorizations. So x squared we only calculate it once. And then we create a sequence, error function sequence, that sums up this sequence to n terms in this very clever way. So we start with 1, right? So if we want to cut this sum at n terms, we basically drop the n plus 1, which is these 3 dots, right? So our last term, and we're summing always, we sum up from last term to the first term, right? So the last term becomes 1 when we drop the n plus 1 term. And then for int I equals n, I greater than 0, and I minus minus. So remember, nth term, n minus 1, so I equals 1. I 0, we don't need to calculate it. N equals 0 because it's always 1. We always subtract 1 minus the value, right? So this 1 minus is common, so we don't go to I equals 0, right? So the result, we calculate the result at each step, which is here, and then multiplied by x squared, which is our val, times 2i minus 1, which is in a numerator, over 2i plus 1, I times 2i plus 1. So this 2i minus 1 is this odd number 5, 2i plus 1 is this 7, for example, in this k equals 3, and then I is the one that accumulates for the factorial in each term. This is an extremely clever and efficient way of summing up this very non-efficient series, right? And then we evaluate the series at 100, 200. We will look at the convergence of the sequence, and then we multiply it by the lead term, all right? Now for large argument expansion, when x is greater than 4, error function has an asymptotic series, 1 minus e to the minus x squared over x square root of pi, sigma from m to infinity, minus 1 to m, 1 times 3 times 5 to m minus 1 over 2x squared m, right? And then the error function complement is just 1 minus error function. So you drop this 1, it becomes e to the minus x squared over x square root of pi, the summation. And in fact, note that first of all, error function is an odd function, right? So we don't need to, if we only need to calculate for positive numbers, and then for negative numbers, we just return the minus error function of minus x. Now this series works for both real and for both positive and negative x, because it has x squared, so this series is always positive, and there is x here, so it automatically reverses the sign. So this automatically gives us the fact that error function is an odd function, right? But here we don't see it immediately. That's because in this large argument expansion, the underlying assumption is that x is positive. X, so I'm going to write it, x is positive here. Okay, so x was supposed to be positive when this series was derived. So for negative x, we don't use this series, we just use the fact that error function is an odd number. Okay, so error function of minus x is minus error function of x. So for large argument, we put this test in the beginning. If x is negative, we calculate minus error function of minus x. And now x is positive, and minus x is positive because x is negative. And we don't need to calculate many terms. It turns out that even 3 terms gives us a very, very good accuracy. So here I'm calculating a0, which is 1, this term, a1, which is point over val, and val is x squared, right? And then a2 is 0.75, which is 3 here, over 2 to the 2 power, so 3 over 4.75 over val times val, which is x to the 4th power. And then a3 is when we set m to 3, x6, so val times val times val, and we end up with 15 over 8, which is 1.875. All right, so these are the terms, and then I have 1 minus the lead term. The lead term is exponential of minus x squared over abs of x. I mean, we don't need to use abs here because we already know how to deal with when x is negative, but I'm putting it here for more clarity. Times the square root of pi. And again, the lead term we only calculate once, so a little bit more efficiency. And then 1 minus, note that the sign alternates from positive to negative. So 1 minus the lead term times a0 minus a1 plus a2 minus a3. All right. And this gives us a very, very good accuracy for large x. So let's look at the shape of the error function. And of course, I'm going to compare it with the Python implementation. And again, what I like to point out here, Python doesn't have any pure Python implementations. All of the SciPy packages, especially the special one that evaluates a special function, these are all Fortran and C codes that they're using Python. Basically, Python is just a wrapper. So whenever you evaluate something using the special functions in Python, it just runs the C code or C++ code or Fortran code and then gets back the result. So Python doesn't have any implementation, and it makes sense. If you implement any of these special functions in Python, the evaluation is very slow. It doesn't make sense to implement any mathematical functions in Python, in pure Python. Python is just a wrapper, so I mean, that's a no-go for me in terms of programming scientific computing in Python, because I want to take advantage of the language itself, not the fact that it's just a simple wrapper. All right. All right. So error function at minus infinity, it should approach -1. At plus infinity, it should approach 1. And as you can see, it only varies a lot in this interval, -3 to 3. Outside this, we're pretty much there at 1 or -1, right? And that's a very interesting behavior for error function. So at 0, we hit 0. Any odd function at 0 must be 0. And we clearly see the odd symmetry about the origin, right? And here's the code in the test that I wrote to plot this. So error function, new error function, we create our error function object, and then x linear space from -5 to 5, 1000 points. I create a timer and calculate my error function by applying a for loop, and then plot it. All right, so let's head to Eclipse. So I have this error function class that I wrote. For a small argument, we use this sequence and evaluate at 200. For large argument, I use the asymptotic behavior, and then error function. I check if it's less than 4, then invoke the small argument. I check if it's larger than 4, then I invoke the large argument. And then I have this complementary error function, which is just 1 minus error function, so that's very easy to implement. And I have other things like error function for complex numbers, which we will look in the next few slides. And then there's a whole bunch of families of error functions. For example, the scaled error function, complementary. This is the scaled complementary error function. Error function Cx. X means scaled. And you just take the complementary error function and then multiply it by exponential of x squared. Similarly, we can define the other family of functions, and I'll talk about them in the next few PowerPoint slides. But going back to our test class, I have this test error function. I've written many tests, so let's look at test 1. So in test 1, I just create my error function class. Calculate my x values using the linear space, and then create the timer and calculate error function or the complementary error function, and then plot them. So let me just uncomment error function, also uncomment this one, and I'm going to plot both the error function with blue color and complementary error function. All right, so let's hit run. It's very fast. It took only 67 milliseconds to do 2000 evaluations. So as you can see, error function is the blue curve, and outside the -3 we are pretty much there. So it's really very a small variation. Similarly here, as you can see, we're pretty much there at at 1, right? And then the complementary error function is 1 minus error function. So when error function is 0, we have complementary error function 1. When error function is -1, the complementary is 2. So the error function, the complementary error function goes from 2 all the way to 0, right? Now let's export this to Python. Let's call it, for example, test. Okay, and then let's just open it up in a text file, select all of the text, and then go to our Jupyter notebook here, and I'm going to paste them. And then what we're going to do here, so x0 y0 is our error function, and then in the scipy.special package we call the error function of x0, and as you can see, we get a very good match. All right, and y1 is our complementary error function. So if I use 1 minus this, I get the perfect result, and I believe there is also a complementary error function. Yes, x0, we get the perfect result. Okay, so this is how we calculate the error function in a very efficient way. So what about the complex numbers? So for complex number, the evaluation is a bit more complex in the sense that the format changes. We cannot use basically this series that we used for real numbers to calculate the complex numbers. If you recall, in the Bessel function, we could in fact use that series, but here I'm not using it. I'm using this expression, which has a better efficiency and more accuracy. So how does it work? So we write the z if z is our argument, which is a complex number x plus jy. So the error function of z has 3 terms: term 1, term 2, term 3, and term 3 is basically a series from 1 to infinity. Okay, so term 1, so basically the goal is to write the value in terms of the real and imaginary part, x and y. All right, so term 1 is just the error function of real part. So you take the real part, calculate the error function, which we already have done. Term 2 is e to the minus x squared over 2 pi x, 1 minus cosine of 2xy plus j sine of 2xy. All right, so this term 2, and j is the imaginary round number. Term 3 is 2 over pi e to the minus x squared. It has this lead term, and then sum from 1 to infinity, e to the minus k squared over 4, k squared plus 4x squared. And remember, x is the real part and y is the imaginary part, times 2 sequences f of k, which is 1 sequence, plus j g sub k, right? So these are 2 sequences based on k, the index of summation. So f sub k is 2x, 1 minus cosine of 2xy times cosh, the hyperbolic cosine of ky, plus k times sine of 2xy sinh of ky. All right, the imaginary sequence, this g is 2x sine of 2xy cosh ky plus k cosine of 2xy sinh of ky. And this has very good accuracy even for large z. And then one thing that you have to be careful is the singularity of x equals 0 when x, the real part, is 0 for the second term, right? So in this series, x squared is at the bottom, but there is k squared and k starts from 1. So there is no singularity here. But here we have an x in the bottom, in the denominator, and we have to make sure that we handle it when x becomes 0, right? And the way we handle it, we use a sinc function. So basically the trigonometric identity is 1 minus cosine of 2xy is 2 sine squared of xy. And sine of 2xy is 2 sine of xy cosine of xy. And then you factor sine of xy out. Sine of xy over x gives you a sinc when you multiply and divide by y. So sinc of xy. And the good thing about sinc is that when t approaches 0, this sinc becomes 1. So it automatically handles the singularity, right? So here's the full implementations that I have done. X is the real part of z, the complex number. Y is the imaginary part. Coef is e to the minus x squared over pi. And the reason I'm calculating this here, because it actually appears both here, e to the minus x squared over pi, and in the next term, e to the minus x squared over pi. So for numerical efficiency, I'm just calculating it once and using it everywhere. So term 1 is just the error function of the real part, which we have already done calculating it. Complex term 2 is coef e to the minus x squared over pi times y times sinc of xy. So y times sinc of xy is just sine of xy over x, which I said we can factor this one out using the trigonometric identities. And then sine of xy plus j cosine of xy. All right. And then we have to evaluate this sequence, right? So the real sequence, I call f sub k, I call it the resequence, real part. N goes to 2x times 1 minus 2x minus 2x cosine of 2xy times cosh ky or ny plus n times sine of ny sinh of ny sine of 2xy, and similarly the imaginary sequence. And then we want to create this series for some terms, let's say 50 terms. So I create another sequence for summing the real part, resum, and this goes to series.sum. M goes to this lead term e to the minus m squared over 4 m squared plus 4x squared times the real sequence, and I sum it up from 1 to n. Similarly, I sum up the imaginary part. Okay, and then term 3 is 2 times coef, which was minus x squared over pi, times the evaluation of the summation of the real part plus j evaluation of the summation of the imaginary part at 50 terms, and then we add them together. All right, so let's head to Eclipse. And before going to Eclipse, let me show you the next slide. So this is the complex error function. So again, error function for complex number has 3 terms. And here I'm plotting the x plus j. This x is the real number that I'm varying plus j. So I'm creating complex numbers whose imaginary part is 1 for x between minus 5 and 5. And we have our implementation has high computation efficiency, is pretty fast, and it has very good accuracy. So here's the code that I wrote. X goes from minus 5 to 5. Error function at I, which is a complex array, is evaluating the error function for complex numbers xi plus j, right? So all these complex numbers, the imaginary part is 1, and then I plot it. So the red one is the imaginary part, this blue one is the real part. Now you see the real part can actually oscillate and get out of the minus 1 to 1 range. And this is a comparison between my Java implementation and Python, which is, again, it's a wrapper for the C code that actually does the computation. And you see we get a perfect fit. So let me head to Eclipse. And so test 10 is basically where I calculating the complex values, right? So from minus 5 to 5, It actually takes more time, obviously, because we need to do more evaluations. One evaluation of the error function itself, so it takes time, and then also the series to sum up. So it definitely is less efficient for complex numbers than real numbers, right? So let's look at this. So you see the real part can get out of the -1 to 1 range, and that's where the imaginary part is actually very large, right? And let's export this to Python. Let's close this one and open it with the text editor. Select all of the tests and then go to our Jupyter notebook. So again, we have two plots, x0, y0, x1, y1. y0 is the real part, y1 is the imaginary part. All right, error function. So this is our good old error function. This is the real part of the complex ones. So in order to calculate this, I have to call the numpy.real part, all right? But then I have to add the j, right? So I have to convert this x0, which is a list, to a numpy array, because operators are overloaded for numpy's array, and then I add the 1j to it. And as you can see, we get a perfect fit. If I switch to imaginary part, then I need to plot y1, which, as you can see, we get a perfect match. All right. So the last thing I'd like to talk about here is, let's see how much is the accuracy of our implementation. So let's call this test 14. And public static void test 14, and here I'm going to create a complex number. Z is 2 minus 0.5 times j, all right? And then complex u is I need to create my error function first, and then func.error function z, and sysout u.real, and then sysout u.image. all right, so let's run this. So this is the real part and this is the imaginary part. Let's fire up our Mathematica. So error function and 2 minus 0.5i, 1.0035 minus 0.004749. So it seems we have good accuracy. Let's look at the real part, full digits. 1.003502243313037. So as you can see, we get perfect match, right? What this means, let me also look at the imaginary part first. Does it have the imaginary part? Minus 0.44, minus 0.0047409033129 all right, so we get about 3, 6, 9, 12, 15 decimal places of accuracy that matches Mathematica. So basically what this means is that Mathematica is also exactly using this equation for complex numbers. And that's not surprising. This is because this is the standard way of calculating error function for complex numbers, okay? So our implementation of the Bessel of the error function for complex numbers is very fast, and it's also has the highest possible accuracy that we can get, right? So I hope you enjoyed this lecture. Please stay tuned, and I'll see you in the next one.